Hello everyone and welcome back. In today's video, we're going to start to talk about what derivatives look like for functions of more than one input variable. I'm going to go back briefly and review some of the important concepts for derivatives of single variable functions. So if we had a function of one input variable for y equals some function of input x, if someone talked to us about the derivative f prime of x, then that was equivalent to a ratio. We changed the input slightly using the symbolic notation dx. This represents a small, an infinitesimally small increase in the inputs called x. And then we looked at the effect of that small increase of the inputs. What effect does that have on the outputs? And that resulting change in the outputs is the dy in the numerator of this expression. So if we kept this definition in mind, that allowed us to get some information about the derivative of a function just from the function's graph. If I identified a point on the curve, for example, here, marked by x1, I could ask the question, what is the sign of the derivative of the function at this location? To answer this question, I would move a little bit along this curve in the positive x direction, move slightly to the right, and then I would analyze, is the curve increasing or decreasing as a result of that movement to the right? At the point x1 that we've marked, increasing the x values slightly results in the outputs going up. So as a result of that, I would conclude that the sign of the derivative is positive at that location. X up results in the y values going up. If I mark a different point on this graph, the derivative can have different behavior. In this case, if we ask what is the sign of f prime at x2, in this case, my answer would be that the sign of the derivative is negative. And the reason is that as I increase my x value slightly and move along the curve slightly to the right, slightly in the positive direction, I see that increasing x results in the y values going down. So that ratio is negative because an increase in x resulted in a decrease in y. Finally, I could ask about a third point on this curve, this point up here at this local maximum, which I'll call x3. And I can ask, what is the sign of our derivative at the point x3 at this local maximum? In this case, we would say that the sign of the derivative is 0. And that's because at this location, if I increase x ever so slightly, my y values don't really change at all. If I'm located here at a local maximum or at a local minimum, the tangent line to the graph is horizontal. A very small increase in x results in essentially no change in the values of y. Now let's take these definitions and these ideas and bring them into the multivariable context. If I have, for example, a function of two input variables, a function of x and y, whose outputs are being stored in the variable z, Because this function has two input variables, it's going to have two derivatives associated with it, two what are called partial derivatives. The first derivative is going to be focused on the effect of the first input variable, x. And the notation for this partial derivative is f with x as a subscript. This derivative is also going to be looking at a ratio of a small change in x. What is the effect of a small change in x on the outputs of the function? So we increase x a little bit, and then we study the effect of that increase on the outputs of the function, here called z. Now, notice that when we're writing down the expression for a partial derivative for a multivariable function, the symbols used in the fraction are a little bit different than the ones that we used for the function of one variable earlier. For a function of one input variable, the symbolic notation was dy over dx. And what we've written down here is the symbolic notation delta z over delta x. This little swoopy guy here is a lowercase Greek letter delta. So this is the notation that's used when dealing specifically with a function of two input variables, and we're calculating a partial derivative. Delta z over delta x, this lowercase delta. Now you can probably anticipate what the definition will be for the partial derivative in the y direction. Here, we just increase our y a little bit and study the effect of y on the outputs of the function. So a small increase in y, and then in the numerator, here is the effect of that increase on the outputs, the resulting change in the z values. So here are the definitions of the two partial derivatives for a function of two input variables. And you can imagine perhaps that a similar definition would apply if you were dealing with a function that had three input variables, or four input variables, or five input variables. So now let's think a little bit about the graphical significance of the derivative for a function of two input variables. To begin with, let us go to Desmos 3D and have a look at the graph of an example multivariable function. So here the multivariable function that we're considering is the one that's given by the formula z equals 3 minus x squared plus y squared. So it's a hyperbolic paraboloid that's been shifted up by 3 units. Now I've marked a certain point on this hyperbolic paraboloid, this dot right here. And I would like to think about what the derivatives of this function are doing at this location. To answer that question, I can consider what happens to the heights on the graph, what happens to the z values on the graph, as we move from this location a little bit in the positive x direction. Now, the positive x direction, as pictured here, is moving off to the right. And what I can see is that as I follow this graph in the positive x direction, my heights and my z values are beginning to go down over time. So from this location, increasing x a little bit causes a decrease in the z values. As a result of that, I can conclude that f sub x is negative as calculated at this location. F sub x is negative because decreasing z's result from increasing x's. Now the positive y direction is over here in the back. And so if I wanted to study the partial derivative in the y direction, if I wanted to study f sub y, I would just have to think about if I moved from this point in the direction of positive y, what happens to my z values? So if I start at this point and move slightly in the positive y direction, then I find myself following the surface upward, and those points are getting larger and larger z values as I move in the direction of positive y. So as a result, I would conclude that f sub y is positive at this location because increasing y a little bit resulted in an increased z value. So to summarize what we just discussed, if you want to deduce what the partial derivatives are doing from the 3D graph of a function for f sub x from the given starting point, move slightly in the positive x direction, and examine the effect on the z values. If the z values go up, your partial derivative is positive. If your z values go down as a result of the movement, then your partial derivative is negative. So it's exactly the same as it graphically was in the single variable context. And f sub y is similar for f sub y from your starting location, move slightly in the positive y direction, corresponding to an infinitesimal increase in the y values. And look at the effect of that movement on the heights of the point on your graph. Since the z values are contained and encoded and stored within the graph's height. Let's also examine this idea in the contour map, which we remember is a two-dimensional representation of a three-dimensional surface. Written in the xy plane, and the heights of the different points on the graph will be communicated by using labels on level curves and elevation curves in the graph. So let's suppose this image describes the contour map for our function. And let's suppose that I mark a certain point on this contour map, say this point right here, which I will call P1. And I can ask, for example, the question, what are the signs of the partial derivatives as calculated at that point, calculated at the point P1? So I can say, for example, what is the sign of f sub x as calculated at this point? Now, once again, f sub x corresponds to increasing the x values slightly and studying the effect of that change on the z values, on the output values. So in this image, starting from the point P1, I'm going to consider the effect of a slight movement in the positive x direction, which is slightly to the right in this image. If I move from the point P1 slightly to the right to correspond to a small increase in the x values, I see that that movement takes me away from the level curve z equals -2 and toward the level curve z equals -3. So this is a movement from z equals minus 2 toward z equals minus 3. As a result, moving in this direction causes my z values to decrease, going from a negative value to an even more negative value. Because the z values are decreasing as a result of this movement, I would conclude that this partial derivative calculated at this location is negative. Negative because the outputs went down. Similarly, at that same location, I can ask what's the sign of the partial derivative in the y direction? Now, a partial derivative in the y direction corresponds to a slight increase in the y values, which would correspond to a small movement vertically straight up. And I can see in this image that a small movement vertically straight up is going to take me from the level curve z equals minus 2 toward the level curve z equals minus 3. Once again, from minus 2 toward minus 3. So the sign of this partial derivative would be negative because increasing the y values a little bit caused the z values to go down. So let's move our point now to a slightly different location. And in particular, I would like to consider what happens with the point P2, which is directly on the right edge of this circular level curve, z equals minus 1. And in particular, I would like to consider the effect of a slight movement straight up at that location to help me to find the sign of the partial derivative in the y direction at that location. Now, in order to get a more accurate sense of what's happening in this image, I'm going to go ahead to Desmos 2D, and I'm going to draw a circle in 2D, and I'm going to mark a point on that circle, which is directly on the rightmost edge, so that we can zoom into that digital picture and study it more closely. I've gone ahead and recreated that image digitally to get a more perfect circle. And on the right edge, I've marked that point, which in the handmade drawing we called P2. And remember, our goal is to try and study the effect of a small movement in the y direction upon the z values in this image. Now, when we say a small movement in the y direction, we need to understand that that is a very small movement in the y direction, infinitesimally small. So if I'm thinking about a tiny movement from this edge of the circle in the vertical or y direction, I most accurately really should be thinking about zooming this picture way in to decrease the scale and to decrease the size of the image that I'm looking at, right? Infinitesimally small change in y, extremely small change in y. So I've zoomed way into this picture so that I can more easily see the effect of a very small change in y. Here, the change in y is going to be on the order of 0.0005 units. And in truth, an infinitesimal change in y is even smaller than that, but this is small enough to serve our purposes. I'm going to go ahead and grab a screenshot of this image and paste it into the OneNote so I can draw on it. Okay, so here is our very zoomed in picture of the point P2 as resting on the right edge of the z equals -1 level curve. So the point P2 in this image is this point here, and this red, now apparently vertical line, is the level curve z equals -1. So now in this image, I can represent a small, small, small movement in the y direction by a vector straight up. This is a small, small movement in y direction. And what do I see? If I move a very small amount from the point P2 in the y direction, I'm still basically on the same z equals -1 level curve that I was on at the start. Because I zoomed in so much to reflect an extremely small movement in the y direction, that z equals -1 level curve completely straightened out and became a perfect vertical line. So I see that I'm still at z equals -1, so there's no change in the z values. The reason for this behavior is that at the point P2, the direction, the y direction, was actually tangent to the level curve. If the direction that you are considering for your partial derivative is tangent to your level curve, in such a situation, a very tiny movement will result in essentially no change in the values of z. If you're in a situation like that, where your direction and your level curve are tangent, then the z is not changing at all. Z remains constant, and so the derivative is 0. When you think about this situation, I want you to be thinking about this case in the single variable world. In the single variable world here, we had a derivative of 0 because a slight movement in the positive x direction of movement to the right was actually tangent to the curve at this location. So if we move slightly to the right, our outputs basically don't change at all. And so we get a 0 derivative from this point. And exactly the same thing is happening here. At the point P2, the y direction is tangent to the level curve. So a very small movement in that direction keeps you on that level curve, and so your z values basically don't change at all, resulting in 0 for the value of the partial derivative. The last thing that I would like to talk about in this video is how to calculate partial derivatives if you're given the formula for a function. So for example, if I'm given x squared times y plus sine of x times y plus y cubed, what would be the formula for the partial derivative in the x direction? Now to calculate that partial derivative, I'm going to go back to the original definition of this partial derivative. F sub x asks us to study the effect of changing x on your outputs. When you calculate the partial derivative with respect to x, notice that only x is being adjusted. Only x is changing here, y is not changing. Because y is not changing, when you're calculating the partial derivative with respect to x, you can treat y as if it's a constant. And so that is the principle that we're going to use as we calculate f sub x from this formula. When calculating f sub x, X is the only variable, so treat y as constant and take the derivative using the regular calculus 1 rules that you learned some time ago. So for example, if I want to calculate the derivative of the term x squared times y, in this situation, y should be understood as a constant. So when I have x squared times y, it's not really any different than x squared times 5, for example, 5x squared. So I would calculate the derivative of y times x squared the same way I would calculate the derivative of 5 times x squared. I would copy paste the constant multiple, and then I would take the derivative of the x portion using power rule. Let's think about this next term here. Sine of x times y. In your mind, try and think about this as the same as sine of 3 times x, because y here is acting just like a constant. If I take the derivative of sine of 3 times x, in that situation, I will need to use chain rule. I will need to keep the derivative of the outer function, turning that sine into a cosine. And then I will need to take the derivative of the inner function, the derivative of x times y. The derivative of x times y with respect to x is just going to be the constant multiple y. And that's just once again following from constant multiple rule. In the back, we have a term that does not contain any x's. We have a term that contains only y. So for the purposes of this calculation, this term containing only y is a completely constant term, acting something like plus 7, for example. And when you take the derivative of a constant term, when you take the derivative of something like 7, the result of that is going to be 0. So this expression right here, f sub x equals 2xy plus y cosine xy plus 0, is going to be the derivative of this function with respect to x expressed in terms of a formula. Now, to calculate the other partial derivative, we're going to use a similar idea. In f sub y, only the y is changing. The x is not changing, the x is constant, so we can treat the x like a number in our calculation of the derivative. Taking this one term at a time, if I want to take the derivative of this first term, where y is the variable and x is the constant, then if I use constant multiple rule, the derivative of x squared times y is just going to be x squared. The same way that the derivative of 8y would just be the constant multiple 8. The derivative of sine xy, once again, would require us to use chain rule, starting by taking the derivative of the outer function, which turns that sine into a cosine. And then we'll take the derivative of the inner function. X is the constant, y is the variable. So the derivative of this inner function with respect to y is going to be the constant multiple x as a result of constant multiple rule. And if I'm taking the derivative of this term in the back, y cubed, where y is the variable this time, here I just need to use power rule. bring a copy of the exponent to the front, and then decrease the exponent by 1 unit. So here is the derivative of my function f with respect to y. This formula will give us the derivative in the y direction. Now, just like ordinary derivatives, these partial derivatives can be taken multiple times. So for example, I could ask for a second derivative, denoted here by f with a subscript of 2 x's, f sub xx. What this is asking me to do is take the first derivative in the x direction, and then take another derivative with respect to x again. So I need to take the derivative with respect to x of the partial derivative with respect to x I found earlier in this problem. Let me just go ahead and copy paste it. So now, taking the derivative with respect to x a second time, we see that 2xy becoming 2y, once again by constant multiple rule. And we see that cosine xy becoming negative y squared sine xy. The chain rule is happening here, which is turning the cosine into a negative sign. That's the derivative of the outer function. And then the derivative of the inner function with respect to x is what's causing another copy of y to pop out to the outside. So this would be the second derivative of f in the x direction, f sub xx. Take the derivative with respect to x twice. For our final example, I could also ask for the second derivative, but I want here to take the derivative with respect to x, and then subsequently take the derivative of that with respect to y. So I would need to start from the derivative with respect to x that we calculated in part A. But this time, for our second move, I'll be taking a derivative with respect to y as opposed to a second derivative with respect to x. So thinking about this in terms of y being the variable and x being the constant, here, we're going to get from our first term 2x, because here 2x is our constant multiple. And to find the derivative of the term in the back, we're going to need to use product rule, because now y is our variable, so that term in the back is a product of something containing y times something else containing y. So we need to use product rule as opposed to constant multiple rule, because this is two variable quantities multiplied together. So following through on product rule, we get the first function times the derivative of the second function, where the derivative of cosine can once again be found using chain rule.
Editing Sam here. At this point, I lost audio due to an encoding error, so there will be an AI narrator for the last few minutes. To finish, we find the second term in the product rule expression, which is the second function, cosine of xy, times the derivative of the first function, the derivative of y being 1,